Alright, so we are going to explain inertia and how inertia is related to mass. We're going to describe the type of force needed to overcome an object's inertia and why. We're going to explain how Newton's first law is a description of an object's inertia. In other words, relate inertia to Newton's first law. Alright, so you have your first box. I'm talking about this line right here. Inertia is box 1. So we want to fill that in with the right answer. So inertia is it A, the amount of mass an object has, B, an object's resistance to a change in motion, C, a force that causes objects to slow down and eventually stop, or the relationship between an object's mass and the amount of gravity acting on it. So if you paid attention to the song, you should know that the answer is B. So what I need you to do is in that first blank where it says inertia is, you're going to write an object's resistance to a change in motion. Go ahead and pause here if you need to, but in that first blank on box number 1, an object's resistance to a change of motion is your answer. That is the definition of inertia. Alrighty, let's move on to box number 2. It says that an object in motion stays in motion, and then an object at rest stays at rest. And then it says, unless acted on by an unbalanced force is the next one. So you should have an object in motion stays in motion, an object at rest stays at rest unless acted on by an unbalanced force. And we talked about unbalanced forces already, so you should remember that an unbalanced force causes a change in motion. So basically what this law is saying is this. Objects want to keep doing what they're doing. If the object is already moving, it wants to stay moving. If the object is at rest, it wants to stay at rest. So here's a very common example that they like to test you over. This is page 3 on your notes. Okay, so let's look at this lady here. Let's look at example A, which is this side. Okay, so in a crash, the woman has a blank force on her body, the seatbelt, to keep her from flying out the window. So you've all been in a car with your parents before. You've been on the freeway, and let's say all the lights in front of them are starting to turn red. People have their brake lights on. That means traffic is getting ready to slow down. Well, what usually happens if you're going at a fast speed and then they hit the brakes? Your body moves forward. But what keeps you from continuing to go forward is your seatbelt. Your seatbelt acts as an unbalanced force. I'm kind of having to abbreviate. It acts as an unbalanced force to keep your body from flying out the window. So like in this picture, she's driving along her merry way. Then she had hit the brakes. And so her body is flying forward because her body was moving with the rest of the car. And so when she hits the brakes, that changes the motion of the car, but her body still wants to go forward. Now let's look at example B over here. Okay. Now you notice something different. It says in a crash, the woman does not have an unbalanced force on her body, the seatbelt, to keep her from flying out the window. So this time she's driving along without her seatbelt on, and she hit the brakes, and so her body still wants to travel as fast as it was going before, and this time no seatbelt, out the window she goes. Hopefully she didn't die. Alright, let's go ahead and go to box number 4. It says objects with balanced forces have an equal number of forces acting on them in all directions, so there is no change in motion. That goes back to when we just talked about balanced and unbalanced forces. And then objects with unbalanced forces have an unequal number of forces acting on them, so there is a change in motion. So if your forces are equal, moving in opposite directions, everything is balanced. If your forces are unequal and moving in opposite directions, you're going to have an unbalanced force. Just that simple. Alright, go to page 5. This is what you have. Let's see if you remember what the answer is. Inertia is, if you said B as in boy, you remember the correct answer. It is an object's resistance to a change in motion. Make sure you circle the correct answer. In fact, I want you to circle the whole thing. Let's look at this example of a inertia. Okay, so here's this dude. Oh, he fell. Okay, why did he fall? Because he's traveling in the subway, and so his body is traveling the speed of the subway. As he forces open the doors, he doesn't realize he's got to get out, but as soon as he takes a step out, his body is still traveling the speed of the subway. That is why he falls over. He's trying to stop his original motion. Objects want to keep doing what they're doing. All right, let's look at these pictures here very quickly. One thing I need you to remember is that the greater the object's mass, the greater the object's inertia. What that basically means is this. A smaller object is not going to have as much inertia as a larger object. So I would think about it this way. Would you rather have somebody throw a softball to you or a full-grown adult elephant? Well, duh, the softball. It's smaller. Okay, so when it's thrown to you, it's not going to come at you with much force. But if somebody catapults an elephant at you, probably not going to make it, because the mass is going to be so great that once the elephant gets to you, it's going to feel much heavier than what it actually is. So I want to look at these pictures real quick, and let's just put them in order from smallest mass to greatest mass, or smallest inertia to greatest inertia. So if you look right off the bat, I bet you knew that F is probably the smallest thing. So that's number one. Okay, what's next? This box. Yep. Next biggest thing, the little bitty smart car. I call those death traps. I would not want to be in one of those. And then, my truck. Yep, it's definitely getting a little bigger. Okay, so I'm stuck with D and C. So if I pay attention here, I've got this rock and I've got this piece of construction equipment. But if you see this, I don't know if this is a person or a lighthouse. Doesn't matter. But if I look at whatever this object is in relation to this, that rock is huge. So I'm going to go with D being next and then my rock being last. And look at me, I'm brilliant because these are the right answers. So this one has the, I'm moving the screen. This one has the least inertia, and this rock has the greatest inertia. All right, let's do box number 6. It says when forces are balanced, there is not, I want to turn my pen on, there is not enough force to overcome the object's inertia and change the motion of the object. So look at this picture example I got down here. This dude is holding up a sign that says inertia. Okay, so his body is at rest. It wants to stay at rest, and so there's not enough force to change the motion of his object. So he is showing you that inertia is at work. His body's at rest. It will stay at rest unless something changes that. All right, when forces are unbalanced, there is enough force to overcome the object's inertia and change the motion of the object. So here we have a ball. It is at rest. It will stay there until an unbalanced force moves the ball. So the unbalanced force is the kick from the soccer player. Football. See, I don't watch sports. And then an object in motion will continue with a constant speed and direction unless acted on by an unbalanced force. So once the soccer player kicks the soccer ball, the ball is going to go into motion until it comes into contact with another unbalanced force, in this case, the soccer net. All right, let's get to box number 8. When objects have a net force that's greater than 0, so anytime the net force is 1 or higher, okay, even 0.5 or higher, as long as it's greater than 0, are there balanced forces acting on or unbalanced? So you should know that it's going to be an unbalanced force. Anything greater than 0 is going to be an unbalanced force acting on the object. And then objects with a net force of 0 have balanced forces acting on them. So that's it. Make sure that you've got all your boxes filled in. Holla.